You're supposed to then make predictions later when you just get X. We've seen a few methods for this: naive Bayes, perceptron, nearest neighbors, and now dual perceptron. It's useful when you have labeled data. Okay? So let's take a break here. And after the break, let's start looking at a different type of machine learning that's not supervised learning anymore. All right, let's restart. Any questions about classification, supervised learning, kernels, nearest neighbors? Yes?
So is the nearest neighbor thing also considered supervised learning?
So is nearest neighbors also considered supervised learning? The answer is yes. So nearest neighbors, you are faced with a problem where you get training examples that have corresponding labels, and you're asked to make predictions about new instances, what their labels are based on what you've seen in the training data. So that's essentially what defines supervised learning. Now, it's true that not a lot of learning is happening in nearest neighbors because you are just looking things up at test time rather than having learned some new representation. But it would still fall under the category of supervised learning approaches to classification. Okay, so classification, nice analogy. It's a lot like test taking. There is something that you're supposed to learn, and then there is test data at the end, which could be an exam or it could be new data. And you haven't seen the answer to that. You try to produce the answer, and you hope that it's indeed the right answer based on what you've learned so far. Clustering is a little different. It's a lot more like, say, baby listening to things. Baby has no clue. It's just hearing all kinds of sounds. And Who knows what they make of it? So what's happening in clustering? It's unsupervised learning, meaning that there is no right answer. You just get data. There's no such thing like a Y, so to say, a class label that you're supposed to predict or that you're being told is the right label. You're just getting, let's say, a bunch of email, but nobody tells you what's spam or ham. You get a bunch of digits, scans of digits, but nobody tells you which one is a 0, 1, and so forth. The goal in clustering is to detect patterns in unlabeled data. So, for example, you could get a bunch of emails and you want to group them. You don't have labels yet, but maybe you just got 1,000 new emails, and to process them more effectively, you want them clustered. You hope maybe that some cluster will emerge that's all related to one topic. You can process them all in one go. Another topic will emerge in another cluster. You can process those in one go, and that could be a use case of clustering, right? Could be for search results. Let's say you are searching for something, and maybe you're searching for something, you have a sentence, and there might be multiple interpretations of that sentence, right? And now there are different types of pages that could come back. And rather than just giving you back the top 10 ranked pages, you might hope that it says, oh, well, there are 5 interpretations. The first cluster is all the pages in the first interpretation. The second cluster, all the pages in the second interpretation, and so forth. Now, we haven't defined those interpretations, so clustering would just do something. It might be the clustering you like or the one you don't like, but that's the idea. If you have a lot of customer data, maybe you are some kind of store, and you want to cluster your customers. You want to get some idea of what types of customers do you have. You might look at their purchasing data. If it's an online store, maybe their browsing behavior, what products they have looked at but not bought ultimately, and so forth. And based on that, group your customers, and then maybe you can start analyzing more easily what the patterns are that you see among your visitors. Another thing that you could do is you could look at program executions. You could look at execution traces, vectorize those in some way, then cluster them, and hopefully you'd see clusters emerge related to normal behavior, and then maybe some other ones that don't fall in any of the clusters where something weird is happening. You want to go check what's going on. So this is useful when you don't know exactly what you're looking for. You just have some data. You hope there are some patterns to your data, but your data is high dimensional. Look, let's be clear. If you had 2-dimensional data, you would just plot it, you would look at it, and that would be it. But imagine your data is 1,000-dimensional, 1,000,000-dimensional. Just plotting it is not really an option, and so now you want some other tool to figure out what patterns, what cluster there might be in your data. Often you get out gibberish. It's part of the deal here because you're not supervising it. You're not telling it what you're looking for. You're just saying, cluster my data into groups, right? All right, so simplest thing, of course, would be something where you just cluster by color, and we'll use that as an illustration as we go along, but really you don't know what you're looking for. So let's say these are a bunch of points, and we're visualizing these in 2D because that's the way we can build intuition, but keep in mind, if your data is really 2D, probably don't have to worry about clustering. Just plot your data and do your analysis. Let's say your data were to look like this, but in some high-dimensional space, let's say. Maybe you'd hope that there would be 2 clusters coming out of your algorithm, these 2 clusters. Now, here it is a very different kind of data, right? And you might want to get out these 2 clusters. This is very different, right? Because you look at this point and this point are quite far apart, actually, but they fall in the same cluster. Right? In fact, these 2 points are closer together than these 2 points. Nevertheless, these 2 are in a separate cluster and these 2 are in the same cluster. What's happening here is something where it's looking at closest neighboring points. If you have a neighbor share with another point, then you're also in the same cluster. So this is something we'll see at the end of the lecture called agglomerative clustering. And then this here is what we'll see, we'll call k-means, will give us this result, which is where you look at localized blobs of data. So one way to measure similarity is look at the distance between 2 points, right? You say, find a group of points that are all close together. So k-means gives you one way of doing that. What's happening in k-means? You pick, so this is the algorithm, you pick k random points as your cluster senders. Okay? So we just did that here. We picked 1, 2, 3, 4, 5 random points. When I say random points, the simplest thing is to pick actually, in this case, 5 of your data points. Don't just randomly generate a point that might be anywhere in space. Just pick randomly 5 points from your data set in this case. And then you alternate. You alternate between assigning data instances to the closest mean. So what does that mean? You'd look at, well, for each one of those points, there are points that are closest to that point, and then the other points. And this actually gives a decision boundary pattern like this here. Everything that's over here, their closest point is that one over there among our 5 centers. And you would assign all of those points to that center. Do the same thing, all points over here, go to this point, this center, and all points here, go to this center. And we do that for all 5 regions, right? You don't have to actually compute those regions. You would actually cycle through your data. For each data point, you check which one of those 5 is the closest, and you assign it to the closest one. Once you've done that, you compute the mean of, for each cluster, you compute, or for each center, you look at all the points assigned to that center, you compute the mean of those points, and that becomes your new cluster center. So if I compute the mean of all the points that lie in this area, be some kind of mean, maybe it'd be over here, and that would be your new cluster center for the first cluster. You do that for all 5 of them. You now have 5 new cluster centers, and you repeat. You now cycle through your training data again, find for each training data point the closest current cluster center. Once you've done that, for each cluster center, you average all the ones assigned to it. That generates the new cluster center. You keep repeating until no points change their assignment anymore. You reach a fixed point, nothing changes anymore. Okay? So cluster centers would move here, and this would then repeat. So here's an example of this in action. We started with 5 center points, randomly chosen from the data. To visualize each of the current clusters, we choose colors. So there's a blue cluster, green, purple, red, black. We've colored everything according to the closest point among our centers. Then we take the average of all blue points, which will give our new cluster center for blue. Same for green, red, purple, black. We get this over here. Then we reassign, recompute the means for each cluster. That will be a new center. And we repeat this until this doesn't change anymore. Okay, so let's look at this again. This is how k-means tends to play out. So we start with just some arbitrary set of points that are our cluster centers. We split the data according to whatever they're closest to, take the mean, new cluster center. We see here that we have the green covering both of those. That's the case for now, but we'll see that at some point that will get pushed out. Same thing here, we'll have this cluster, which we really would think of as one cluster split by 2 centers. But we'll see that actually over time, things will shift around and we'll get a pretty clean split of our data into the clusters that we might hope for. Is this guaranteed to happen? No, this happens to happen here. If we had picked 3 clusters instead of 5, we'd end up with something quite different. We picked 10 instead of 5, we'd end up with something quite different. So there's a lot of choices to be made here that you don't know ahead of time what the right choice is, so you'll have to try many things. So here's a general trick that comes back a lot in machine learning. We're seeing it in the context of k-means, but it's actually a pretty important idea. So that often you have an intuitive notion of what an algorithm could look like this k-means algorithm. It makes sense, right? You assign things to the closest current cluster, you re-average and keep doing this. But are you guaranteed that this will converge, that it will reach a fixed point or not? One way to analyze this is to see if there is an optimization problem that you can associate with what you are doing. Because if there's an optimization problem associated with it, and what you are doing is optimizing an objective, and in every step you're making that score better, then you know that at some point, if that score cannot be infinitely good, you need to reach some kind of limit, and that's your current local maximum or maybe global maximum that you're achieving In this case, we're minimizing your global minimum, hopefully, but maybe a local minimum, and then you can give convergence guarantees that way. Okay? So you can avoid the concept of cycling, right? Because you can imagine, well, what happens if we reassign and so forth? Can we get in a cyclic pattern? Well, if you can show you're optimizing an objective function, that objective function is always getting better. That means you can never land in a cyclic pattern, because a cyclic pattern would mean that your objective function goes back up, comes back down, and so forth. So the objective function for k-means that you can back out, if you think about it carefully, is that we're looking at the sum of the distances for each data point xi to its cluster center cai, where ai is the assignment that we have for data point I. So ai is an index into one of our k cluster centers. Okay. So what are we looking at here? We have points xi, which we can't change. We have assignments ai, which are variables. We can choose any assignment for each data point, assign it to cluster 1, 2, 3, up to k. We have a choice. And then there are the means that we're keeping track of. And we're defining this objective here as a function of all of those. And the claim is that each iteration in k-means will make this objective function go down, meaning that you cannot get into a cyclic pattern that you keep oscillating in. There are two stages in each iteration. There is an update of the assignments, which keeps the means fixed, but changes what you're assigned to for each data point. And there's an update of the means, which fixes the assignments for each data point, but changes the means. So to show that we're reducing this objective in each iteration, what we can do is, if we can show that we reduce the objective in the first step and in the second step, then together they definitely reduce the objective, and we know we're in every step reducing this objective function. Okay, so the first one is updating assignments. What's happening there? The assignment we pick is the minimum over all possible choices of clusters, current cluster centers, of the distance between xi and each of the cluster centers, right? Okay, well, so what that does is, for an example like this, if you have some cluster centers, you'd go to you have a current assignment that computed the means, and then your new assignment will be something like this, where you have the points associated with whatever is closest right now. This is old, this is new. Okay, what's our objective function? Our objective function is the sums of the distances of each data point to its assigned cluster center. If initially it was assigned to some cluster center, and we now assign it to the closest one, that distance can only go down. So very easy to show that distance will always go down in this step of the algorithm, because you pick the closest one. It can never get worse. Second update is updating the means. So what we do there is we say these cluster centers are going to be relocated at the average of all the data points assigned to that cluster center. Right? So we have our assignment. This is old. We have our old cluster centers. If we do this update, what happens is the centers will shift to the means of the corresponding data points. Intuitively, we see that these centers are shifting closer to all of the points here. As a consequence, the score that we're looking at, remember, the sum of the distances should only decrease. It can never go up because we're bringing it closer. Now, you need to do a little bit of math to show this. We're not doing the math on this slide, but effectively, you can show that if you assign your center to be the average of all of the points, that'll be a closer sum of distances than any other location you could put your center at. It's the optimal location to put it at, given that fixed set of points. That's a small optimization problem to solve. You essentially solve an optimization problem, find the coordinates that minimize the sum of distances, and you'll find that it is the average. Okay, so that's what we're using here. We're not proving this, but this can be proved. One thing left now, we know the algorithm. We know it's guaranteed to not get into cycles, but rather keep decreasing an objective criterion, which is a good thing. We still need to initialize, right? We need some initial means to kick this off. It's actually a non-deterministic algorithm because we do this randomly, right? Here is one initialization, which would lead to good results. But things can go wrong if you have a bad initialization. Think about this here. Can you think of a bad initialization? The black ones are the data points. Can you think of a bad set of centers that would lead to a different result that you probably don't want. Well, here's an example. What if you place center here, here, and then the red one over here? That's the grouping you'll get. You'll end up with the clustering that I've drawn there, which is probably not the one you'd hope to end up with, right? Now, if you did this, you would actually, and if you compared what you get from these two initializations, you can actually look at your objective criterion, the sum of the squared distances, right? That's what we're optimizing. And you'd realize that this one, after iterating, will land in a better score than the one on the right. And so you'd run this multiple times, multiple initializations, see which one has the best score, retain that one, right? So a couple of things you can do. We're not going to get into a lot of details about it, but you can essentially look at your clusters. For example, this cluster over here. You can say, well, this cluster has very high variance compared to all other clusters. So maybe I should introduce 2 centers there instead of the 1 center. And now you end up 4 centers total and work with that. And you can do something similar here. You'd say, well, these 2 centers are very close. If I were to merge those 2, it wouldn't change my objective function all that much, only a little bit worse, so let's merge those 2. So there's all kind of tricks you can play there to get this to work better. Either way, you can always end up stuck in a local minimum. You have to be careful about that and use many, many initializations till you have done enough runs to find a good answer, so to say, right? For example, this here is not exactly what you'd want. Again, maybe if you looked at the variance in that cluster, you decide that you want 2 points and it split up. Same thing here. Not exactly what you want. Maybe you'd realize